Maximum likelihood estimation says that good values of theta, like the 55%, should assign high probability to the observed data that I have. And so that's really the motivation and intuition behind maximum likelihood estimation, or MLE criteria. So the purpose of maximum likelihood estimation, as its name says, the maximum of the likelihood function. That is to find the set of parameters which are most likely to have produced the observed data. So let's look at an example. Consider here that I have data generated from a Gaussian distribution. I haven't formally defined that yet, but I think you all know that a Gaussian distribution looks something like this, like a curve, like a bell curve. And assume for a second that the Gaussian distribution has a fixed variance, so the width is fixed. But I'm not really sure about the value of the mean. I don't know where the center point of the Gaussian is. I have some observational data that I've repeated 6 times in these 6 subplots for you. So you can see the histogram of the data in blue, where the legend says data. That's fixed and that's shared among all the among all the subplots. But what I'm trying to do is I'm trying to move this orange line. So this orange line, I'm trying to move it over the data and try to find the place where it best matches my observed data. So putting it in the language of what we said about likelihood, I've made some observations first. Conditioned on those observations, I'm trying to find the parameters which are most likely to have produced the observation. In the case of this Gaussian example, I'm trying to find the mean that is unknown to me by moving this Gaussian over my data and trying to find the point where it best matches. Which one of the Gaussians or which one of the subplots do we think has the mean value that best matches the data? Someone point me to the right subplot.
Fourth one?
The fourth one, right? So this one down here seems to be, at least among the ones that we have on the plot, the best fit or the best choice of the mean for a fixed variance Gaussian that fits my data. In fact, under every one of these subplots is another plot. It's a bit small. It says log likelihood. And we're plotting the values of the log likelihood over these different instances. And the one for this subplot, the fourth one here, has the highest value of the log likelihood. So maybe if we can formalize the log likelihood and try to find the maximum value for it, that value is the one that best describes my observed data. And hence, we call it what? Maximum likelihood estimation. So let's go back to our coin example. Let's say that the likelihood of a coin's bias, or the parameter theta, having observed some number of trials with some number of heads and some number of tails, which were IID, identical and independently distributed trials. This can be modeled using a binomial model. And this is similar to what we saw in a couple of slides back. So the likelihood or the chance of this particular theta having generated my observations is theta to the power of nh, which was one of my observations, and then 1 minus theta to the power of all the tails that came out. For a fair coin, it comes out to this expression here. Later, we'll see that if we don't have a fair coin, it might come out to an expression like this. And then that has some value. And I can give you already the sneak peek that this value is larger than this value here. That's why 55% is more preferred. But already on this slide, you might be wondering, well, this is a really small number. It's like 10 to the minus 31, and it's going to get probably even smaller if I increase my number of trials from 100 to 1,000 or whatever it is. So because these values are pretty small, just like we've done in the past, we use the log likelihoods instead of the likelihoods themselves. So we can write out the log of the likelihood function, now expressed as this cursive L, as nh times the log theta plus nt times log 1 minus theta. So I'm applying log to this expression up here. So given the observations that I have, again, what were my observations? I had 55 heads and I had 45 tails. Given the observations that we have, we can now plot out the values of the log of the likelihood and the log likelihood. So these two are just the same. I've just applied log on it. And what was my goal again? My goal was maximum likelihood estimation, meaning I need to write out the expression of the likelihood given the observations that I have, and then try to find the maximum point of it. And if you recall from a few lectures back, the maximum of f of x, so max, or sorry, not the max itself, but let's just bring it down here. The argument that maximizes f of x is the same as the argument that maximizes log of f of x. Remember, so what we're trying to find is theta. It doesn't matter if I look at the log likelihood or the likelihood. The maximizers are going to be the same value. So if I plug in different values into the log likelihood, let's say I'm iterating over, of course, between 0 and 1 over different parameters theta. For 0.1, I'm going to put it into this expression. That's 55 times log of 0.1 plus 45 of log of 0.9. It gives me some value for the log likelihood. For 0.9, it also gives me another value. For 0.5, gives me some other value. What is the value of the log likelihood for theta equals 0.55? Can someone help me out here? Who has a calculator?
Minus 29.88.
Minus 29.88, okay. Hamza?
Yeah, same thing.
Okay, then maybe I've done it wrong, but the value I get is like 68.81. I'm not sure. Maybe I've done something wrong. Can someone confirm? 55. Oh, I see. Yes. Okay, good point. Hamza, this is log base 2. You've done log base 10. Right? So commonly it's, and that's fine. I think all of the log values that you see on the slide are log base 2, so that's why I get this comparison. If you do log base 10, again, log is it applies things monotonically, so you would get the same relation between all of these values. And what is that relation? The point I want to emphasize is this. The relation is that for the value of theta equals 0.55, we get the highest value of the log likelihood. Remember, all of these values are negative, so highest means the smallest, magnitude here. And what was our purpose? Our purpose was which theta best describes the observations, the one that maximizes the likelihood, which is the same as the one that maximizes the log likelihood, because the maximizers were the same. And so if I have 55 heads and 45 tails as my set of observations, then the best reasonable guess that one can make, purely based on the observations, not based on past experience, which we call prior, just based on these observations, you're thrown into a new world and you're given a coin to flip with 55 heads and 45 tails. In this new world, based on no prior information that you have, the best guess you can make is that it's biased at 55%. That's the most reasonable guess you can make. That is what the MLE, or maximum likelihood estimator, tells us to do. Yes, Manoj.
I'm sorry, I didn't get that. Is it log base 2?
Yes, in the case of log base 2, I think it's 68.81.
If it would be log base 2, the answer would be greater than, like, it would be like minus 90 something, right? This should be log base n to get around this value.
So this value you're saying on the slide is not log base 2?
No, I think it's log base n to get minus 68 something.
Log base n. What is n?
Sorry, e, log base e.
Oh, log base e. Oh, okay, yes,
That's
absolutely. Maybe I'm wrong about the base of the log. The point is that I think at least all of the values on the slide are using the same base. And so what matters is the relation between them. The relation says that the maximum value of the log, in this case of base E, thanks for that clarification, is given at the point theta equals 0.55. I see some faces that are not so impressed because it really goes against your intuition. So ask questions if you don't like what I'm saying. Guru specifically is just annoyed.
No, I think I'm good.
Okay. Okay, cool. So now, one question you might wonder is, well, if I want to find the value of the maximum of the log likelihood function, do I really need to iterate over all possible values of theta between 0 and 1? Is there no easy way to do it? And lo and behold, there might be, which we'll see next. So if I write down the expression first of the log likelihood as this expression here, and my goal is to find the maximum, just like we've done for most optimization problems within this course, we try to find the point at which we have the derivative is equal to 0. That either corresponds to a minimum or a maximum. In this case, it's a concave function, so it will be a maximum point. So setting the derivative of the log likelihood with respect to theta to 0 gives us, in this case, it gives us, what is it? NH over theta plus NT, or is it minus NT? It's minus NT over 1 minus theta. We want to set to 0, and so this gives us some expression, save you the time, gives us some expression, which ultimately gives me the best value of theta resultant from setting the derivative of the maximum likelihood to 0, and that's why there's a subscript of ML corresponding to not machine learning, but maximum likelihood, to the closed form expression here, to the ratio of NH over NH plus NT, which is just N, all the trials that we have. So in this case, we don't need to explicitly plot out the values of the likelihoods and the logs and go over multiple different values of theta, but we have the closed form expression already telling us that the best value in terms of the maximum likelihood estimator is 55%.